Hello everyone, in this video I'm going to go over how we break down and organize the periodic table into two major concepts, and they're going to be called groups and periods. So let's get started. So first off, with this image you can see that you have a periodic table, and then I have two big arrows. One says periods and one says groups. Periods are going to be the horizontal rows that you see on the periodic table. All right, so what we have is periods will be pretty much going down from left to right, and you would have 1, 2, 3, 4, 5, 6, 7 total possible periods. While groups will be the actual vertical columns going up and down. So for vertical groups, all right, I would have, starting with hydrogen here, 1, all the way over to 18. So I'm going to have 18 possible groups. So again, periods are going to be the horizontal rows, and groups are going to be the vertical columns. So let's get more involved with the groups. All right, for a group, as I just said, they're going to be the vertical columns, and there's going to be a total of 18 of them if you count from left all the way over to the right. All elements that are in a particular column or group will be very similar in their chemical properties. So, for example, they'll all have around the same overall boiling point or melting point or ability to conduct electricity. All right, they'll all be similar, not exact, but similar. But for us, the most important piece of information that we're going to need to know is that they will all have what we call the same number of electrons in their outermost energy level. In the next video, I'm going to go over how to draw where all the electrons are located for an atom/element. But for our purposes right now, just think about it. You have a nucleus. In the nucleus are protons and neutrons. All right, remember that's where they have to stay. And then the electrons are going around the nucleus in these orbits or shells, just like planets orbit the sun. So what this information is telling us is whatever the outermost energy level is. So I just drew 2 here, 1, 2. This here is going to be my outermost shell, and it's going to tell me how many electrons should be in that outer shell. And later you'll see that we'll draw electrons as little dots like this. So let's just say I just drew 2 dots. Again, those are 2 electrons. So in theory, the way I drew it, there are 2 outer valence electrons. And that's what that group number is going to tell us. So whenever you hear me say valence shell, that is going to be the outermost ring, or valence electrons. Again, that would be, as I just drew over here, the amount of electrons that are in the outermost shell. Down here in my diagram, I give you a bunch of examples of some of what we call the noble gases that are in group number 18. All right, so in group number 18, you can see that all of the elements, all right, that are noble gases may use a different number of energy levels, but their outermost ring should have theoretically the same amount of valence electrons. The only thing that's going to be different is helium over here. That's going to be an exception, and we'll get to that momentarily. So if I bring this diagram up here again, you can see that I have the majority of the groups or columns color-coded. Everything in the middle right now is just in white because those are all the transition metals, and they get a little funny. All right, their valence electron number could possibly change in contrast to anything you see in the first 2 groups or columns on the left-hand side of the periodic table that we have in red and orange, and the ones we see at the far right starting from both yellow to purple. So if you number them, the first one here would be number 1. And then if I go all the way over to the right, the purple column would be the 18th group. However, that number, especially once you get to the teens, isn't really necessarily telling you what the exact number of valence electrons are. So here's how we can figure that out. And if you have your periodic table printed out, you can make a notation of this on yours as well. So if I start in group 1, like I have up here, again, group 1 should always have just 1 outer valence electron. Group 2 in orange should have 2 outer valence electrons. And how the numbering should go after that, so this will be 2. I would have 3, 4, 5, 6, 7 valence electrons, and then things get a little weird. These next 3 groups would actually only have 8 valence electrons. So each group here would actually have the same outer valence shell electron possibilities. And then you start to begin at 1 again. So then we'd have 1, 2, and then you can see here in the yellow, we're going to have 3 valence electrons, 4 for green, 5 for that kind of aqua color right here, all the way till you get to purple, which is technically the 18th group. But everything down the line here in the purple column will have 8 valence electrons. The only exception, once again, being helium right here, which will only ever have 2. But again, we'll get into that later and why that is. So you want to number that on your periodic table. All right, it technically already is listed, but it doesn't look exactly like the way I just did it. So for example, here is similar to the periodic table that I gave you. Again, you have the groups starting at number 1 over here, going all the way over to the 18th group here. But if you notice underneath, you have another number followed by a letter. That is telling you the true valence electron number. So in group 1, you will have 1 valence electron. In group 2, 2 valence electrons. In group 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, and here's where it gets funny. Groups 8, 9, and 10 really only have 8 outer valence electron possibilities. And then once we get to group number 11, we restart at 1 valence electron. They call it B. So 1B, then in the 12th group, we'll have 2 valence electrons, 13th, 3 valence electrons, 14th, 4, 15th, 5, 16th, 6, 17th, 7, and then the 18th, you can only have a maximum of 8 valence electrons. So the key is you're going to see as we move forward, for most atoms, except for hydrogen and helium, they're always going to want to try to, if they can, go up to a total of 8 valence electrons in their outermost energy level. Now to finish out for periods, which are our horizontal rows going from left to right. All right, not the vertical columns. Again, periods are going to be the horizontal rows. But what they're telling us in particular is this. This is what we needed to keep into account the most. Is that every element that you have in a specific period or row will use the same number of energy levels. And again, what I mean by energy levels is that this is the nucleus that has the protons and neutrons. The first ring would be an energy level where you would find some electrons. Second energy level, third energy level, etc. for as many as you would need. So, down below in the picture here, what you can see is, again, color-coded, the first horizontal row or period in red says that since they're in the first one, they're only going to have 1 ring or shell. The orange period is the second horizontal row across. So any element in that row is going to have just 2 energy levels or shells, etc. all the way down to a total of 7 possibilities. So if this is period number 1, all the way down here in purple would be period number 7. All these elements that we're never going to talk about here kind of fit into that one space, but they're taken out so we can condense the periodic table and not make it as wide. So, for example, sodium, again, atomic number of 11, atomic mass rounded out to 23. Sodium would be located right here on the periodic table. So, what that tells me, first off, it is in group number 1, the first column. So that lets me know that I'm only going to have 1 outermost valence electron. And then it happens to also be in the third period or horizontal row. So that tells me that sodium will need to use 3 energy levels or orbits or shells, however you want to say it. So over here in this diagram, you could see that sodium is going to make use of 1, 2, 3 energy levels, and it's in the third period. And in its outer valence shell, which is this third ring, it only has one electron, which correlates back to, again, here being in the first period, or I'm sorry, the first group or column. So that's what that information is telling you. One last thing about periods is as you move from left to right, the overall mass number will increase as well. So the size and, in theory, weight of the element slash atom will increase as you move from left to right. So let's finish this out for review. So first question here is, how many energy levels or orbitals, those are the rings, will magnesium need to use? So that means what period number is it in? So if I look over at the top example, I'm going to circle magnesium. It's in the 1 to 3rd period. So that means, if here's the nucleus for magnesium, it's going to need 1, 2, 3. So this would be the 3rd energy level that it has to use. And then if I want to look again at overall groups, all right, so it says how many valence electrons will magnesium have in its outermost energy level, shell, orbital, whatever you want to call it. That's going to be the group number. So magnesium is all the way up top again in the 2nd group. So that means it's going to have 2 outer valence electrons. So eventually you'll see in our next lecture that when you were to go draw all the electrons that magnesium has, and it actually has a total of 12, right? I'll teach you that it has 2 in the first, then it's going to have 8 in the second, 1, 2, 3, 4, 5, 6, 7, 8. So we have 2, 8 for a total of 10, 2 more to make 12, and here is where these 2 more are going to be that I just drew out here. And those are its 2 outermost valence electrons. All right, so take this information and apply it to the worksheet that you have this evening for homework. Thank you very much.